And so, any questions? Anything you want to talk about with PA5 network connections, sockets, threads, things like that? Um, I'll get things graded hopefully by Monday, and we'll be able to talk about them more on Tuesday. But anything you want to go over? Any lingering issues up front? Did people mostly figure out the mechanics of sending information back and forth, whether it's a name or mouse click or whatever? Cool. It's a challenging assignment for sure. And once you have the basic mechanics set up, it's really not that hard compared to PA4. But it's all about getting that sort of conduit set up. Starting these things is usually a lot harder than keeping them going. But once you have a pair of sockets connected and you're in sync, then it's pretty straightforward to send back and forth. But the setup can be very challenging. Um, and this is where getting good with writing sample code will help, right? If you've got this whole dots game and you've got all the swing classes and all that kind of stuff, that's a difficult framework within which to try to figure out details of threading or sockets or server sockets. Writing junk code, right, throwaway code can definitely help. Getting pieces working and then trying to put those in. Um, and it's a lot about organization. Just like I said with PA4, right? It's not unusual as you're working through PA5 to say, oh, wait a minute, I should do this differently, and go back and change, where you're constructing things or declaring things or using things and so on. Um, but I've gotten through some of the grading, and so far looks like a pretty good level of success, at least getting some of this working. All right, no other takers. All right, let's talk about interfaces. So think back to 222 when we started developing more data structures. And for example, we made a data structure called a tree. It was a binary search tree. And we talked about different ways to implement a tree. Um, 2,604 lines of code. Well, that's cool. Yeah, it's fun. It's fun to like cat your source code sometimes and count it. Um, it makes you feel better if you're spending a lot of time working on this stuff. Sometimes just to see, I wrote 1,000 lines of Java code last night. That's kind of cool. Um, or sort it and pipe it into unique, and then it'll only count your blank lines once. All right, so think about CSE222. We were talking about different kinds of data structures, and for example, we talked about binary search tree. And what kinds of things did we want to do with a binary search tree? We wanted to initialize it. We wanted to, add a new piece of data. We wanted to search. So initialize doesn't do anything. Add maybe takes an int and returns a boolean to say if it succeeded or not. Search takes an int and returns a boolean to tell us whether or not it found this thing in the tree. Delete takes an int and maybe that returns a boolean saying success or not, or maybe it can't fail. And left node right takes no arguments, returns nothing, but does a in order traversal, and so on. And we talked about sort of the interface that a user program would have to the underlying implementation of your tree. And we can implement trees a lot of different ways, right? We mostly made a node with a left and a right and a data field. But you know, in some cases, the children were called L and R instead of left and right. Or the data field might be called value instead of data. Certainly, none of those decisions that you make as the implementer of this binary search tree package, none of those decisions should affect whoever is using your package. So I'm a user, I go along, I download your tree package, I'm going to have my main program, and I'm going to say something like, you know, tree.init. And I'm going to say tree.add, you know, 15, and tree.add 25, and t.left node right. And I don't really care how you're implementing this tree, right? I do care what these functions do. I want this to initialize an empty tree. I want this to add a 15. This should add a 25. To the right of the 15, this should print out the nodes in order, and so on and so forth. But I don't care how you do that, right? So we talked about this idea of abstract data types. And when we talk about, say, a binary search tree, there's two views of it. There's the view that you have when you're writing the code to implement a binary search tree. And that's, you know, I'm going to have a node, and it's going to have a left and a right, and a data field, and I'm going to have a root, and the root's going to be null if the tree is empty. And you know, all of those details. But then there's the view as an abstract tree, right, as an abstract data type. And that's the view that the person who's using the package cares about, which is there's an initialize method, there's an add method, there's a traverse method. And so in 222 and more so in 223, we can think about the separation between the abstract view of a data structure and the implementation of it. All right, so when we use, you know, something from the linked list class in Java, we don't know how that list is implemented. We don't know what the code is actually doing. Is it making a set of nodes with, you know, a data value and a pointer? Is it a doubly linked list? Is it a circular list? Is it a list at all, or is it really an array like we did in our first 222 assignment, where we just have, you know, indexes that contain other indexes? We don't know, we don't care. All right. When we use the linked list package or class, all we care about is, you know, our interface to it. So we need to know how to construct it. That's a Java thing, but mostly we have these methods. So there's something called add last. It takes an element of whatever type we're storing in the list, and it returns nothing. And that gloms this thing onto the end of the list. And however it does that, we know that if we ask for the last thing in the list, it'll be the last thing that we added at the end of the list. So in Java, sometimes, or other object-oriented languages too, sometimes what we're going to want to do is define an abstract interface to some kind of data structure. And we're not going to necessarily write any code to actually implement the data structure, but we want to define the interface. We want to define an abstract tree and say, okay, if you're going to write code that implements an abstract tree, you've got to have these methods. It's got to have an add that takes an integer and returns a boolean. It's got to have an lnr that takes nothing and returns nothing, and so on and so forth. 1687, pretty good. And that's like a lot of blank lines and comments, which is cool. All right, so in Java, we have a keyword interface. And an interface is like a class, but it doesn't actually contain code. Okay, it lets us define basically, you know, kind of a template for something that's going to implement this interface. And it lets us specify exactly what methods and what signatures of those methods need to be present for somebody to legitimately implement this interface. So let's do an example. Let's think about a shape. Now we know that we can make a class called rectangle, we can make a class called triangle, we can make a class called oval. And these classes would, do different things. They would have different things. An oval might need to have a major and minor axis. Triangle needs to have a height and a width. Rectangle has a length and a height, and so on. But there's some things in common to these. For example, we may want each of these things to have an area method that tells us the area of the shape, and a perimeter method that tells us the perimeter, and so on and so forth. So we could define an interface called shape, and then if somebody wants to make a particular shape, they can say, I'm going to make a rectangle that implements this interface, and then they go ahead and they write the methods that are specified as being part of this interface. So let's just play with this for a minute. So this is an interface. It defines the signatures of some methods that need to be supplied by whatever implements this interface. So it's kind of like a template for any class that's going to represent a different shape. A square, a rectangle, a circle, an oval, a triangle, etc. So instead of saying class, we say interface. That's a keyword. And then we can go ahead and we can basically put in function prototypes. So interface shape, and so let's have a public method that returns an integer called area, takes no arguments. And here's a public method named perimeter that takes no arguments and returns an int. And public and let's have a method called init, which will create initial dimensions for this shape based on one argument, like size. So for a circle, this might be the diameter. For a square, it might be the length of an edge. For a triangle, it might be the length of each side or something, right? And so as the creator of this interface, I'm decreeing that if you want to implement a shape, one of my shapes, you've got to write code for the area, the perimeter, and an initialize method. And you can put other things in there also, and you can actually do whatever you want inside these methods, but these have to be present. So if I want to make my rectangle class, I can say class rectangle implements shape. And now I can just go ahead and do my usual class definition, but the implements is really just putting a constraint on what I write, which is I have to have those methods with those signatures, in addition to whatever else I have. So yeah, it's like a binding contract. So I'm going to have my usual height and length, and I'll go ahead and make a constructor. So I can construct, in the usual way. And then I've got to have this area method. and I gotta have this perimeter method. Alright, so there's an implementation of a class. The only thing that's different from a regular rectangle class is that I said I'm implementing a shape, which means if I try to compile this, it's going to complain at me that I forgot to make the init method. And if I'm going to do a shape, I've got to have this initialize method. Takes an integer, returns nothing. Now there's nothing in the description of the interface that says what these methods have to do. Alright, so now I can compile this, and then if I wanted a main program, I can do my usual business. So I can make a rectangle and I can call the area method. And this is all stuff we've seen before. So that's really just a way to define what you want your interface to be. And we've done this already. When we implement, mouse handlers and things like that, and we say, or Window Builder creates code for us that says, this is an event listener, right? What we're doing is we're describing an interface, and an event listener, for example, is an interface that, well, it's a placeholder. Right, so a mouse listener needs to implement a clicked, and entered, and exited, pressed, and a released methods. And if you implement all 5 of those that accept mouse events and return void, you've got a legitimate mouse listener. Right? You can do whatever you want inside these methods, but these have to be present. And then things are set up so that, for example, if you want to, make something that picks up mouse events, it's got to implement a mouse listener. Let's see, I've thought about this issue for a long time. What is the difference between an abstract class and an interface? And what is the practical purpose for an abstract when we have interfaces? I don't have a good answer to that. And I actually spent a little bit of time Googling. And what I discovered is that there are bottomless rabbit holes online on that topic and similar topics. And I don't have a good answer for that. And I have never actually used an interface or an abstract class that I've written in my experience in Java. So, but that's just my lack of experience, I think. I just haven't had to use it or known that I had to use it. Yeah, good question. Was the init command a script you wrote? Yeah, what is init? It's a silly thing. Yeah, it's just a script. So it defaults to main.java. If you give it a name, it will use that. It'll pull off an extension on the end and put .java on there if it needs. It'll make sure it doesn't already exist. And then it basically just copies a template into that file. And then changes the name of the class to match whatever the file name is. because I got tired of typing, but mostly I got tired of typing and making typos while I'm typing and then having to correct them. Let's see, many circular methods and whatnot that accepted methods of different types because they're implemented in the main class. Yeah, makes sense. All right. So that's an interface, and like I say, we've been using them when we implement mouse listeners or event listeners or things like that. But mostly we don't really have to think about them too much. I've looked at your house thing before. That was cool. Yeah, I like that. All right, so let's talk about generics. So again, we've used generics, and I promised you we'd talk about how to create generics. So quick refresher, right? You make a hash map. And a hash map basically deals with a pair of items, a key and a value, right? So we have key value pairs. If you code up a hash map, you discover that the code is pretty much agnostic to the type of thing that you're using for a key or a value. In other words, whatever your key is, you run it through some kind of hash function to create an index into an array typically, and then you go down to that location in the array, and maybe that starts a linked list, and you move down the linked list and you look for a data value that matches the key that you're working with, and when you find that key, you take the value in that linked list. That's the value. Or if you're storing a key value pair, you do the same thing. Key goes to an index, follow the linked list to the end, and then put your new value in a node at the end there. Concurrent hash map, cool. Interesting. Yeah, I'm going to do some multiplayer dots later. So rather than make a hash map class for integers and one for strings and integers and one for strings and so on, right? Hash map is a generic, and when you construct a hash map or declare it, you specify inside angle brackets two types, right? This is the type of thing that the key is. This is the type of thing that the values are. And the advantage of doing this is that when you're writing the code for a hash map, right, you can write this code once in a general way, generic, in a general way that whether you want a hash map, where your keys are strings or integers or linked lists or images or whatever, right, you can reuse the same code. You don't have to make a separate class where the keys have a different type. So let's just generalize our code. So let's see how to do that. I turned my ringer off and it's still making noise because volume buttons aren't a thing. Okay, so let's play around with generics. So let's make a stack class. All right, so we're going to make a stack, and we're going to build the stack using a linked list. And the idea is when we push, we're just going to glom a new node into the beginning of the linked list, and when we pop, we're just going to read the first thing in the list and remove it from the list. And the nice thing about linked lists is if we work from the beginning, we never have to worry about any of this other stuff. We have to tweak what this points to, depending on whether we insert or remove that. But we never have to change anything else here. So we could have a million things in this list, and it doesn't cost us a million operations to push or pop. So super efficient if we do this as a list. And I'm going to have a root. Well, let me call it a top of stack, which refers to this first node. And I'm not going to use a sentinel. So if my top of stack is equal to null, then I have an empty stack. So we'll have an edge case, but that's okay. And so let's first make a stack of strings. All right, so Alright, so what do we need in our stack class? Well, we need to have the top of stack, and that's going to be a node. So I'm going to do node top of stack. And I'll put a note here saying this is going to be null if the stack is empty. And we're not going to worry about anything in particular when we construct, so we're just going to do a push and a pop method. All right, so let's do void push string data. So we'll create an empty node. We'll set the data field equal to the data that we're trying to add to our stack. And then we'll say temp.next equals root. So if root is null, this will be our new root, and it won't point to anything. It'll point to null. But if there's already some stuff in our stack, this node that we're creating temp is going to point to that current collection of things. And we'll set our root equal to temp. And that's probably all we need to do to push onto the stack. So that's just inserting in the beginning. And then we'll make a pop method. And I'm calling this root, but I should call it top of stack. So if we try to pop and the top of the stack is null, that's a stack underflow. And we'll just return null and let whatever happens after that happen, which will probably be bad stuff. Otherwise, okay, so how do we pop? We want to take what the current top of stack is, that's what we want to return, and we want to change top of stack to point here. So how are we going to do this? We're going to return top of stack, but before we do that, we want to change top of stack to be top of stack next. And once we do that, we can't return top of stack because now it's pointing to that. So we'll set a temp equal to top of stack, and we'll return temp. All right, so we're going to put temp right here. We're going to change top of stack to point here, and we're going to return this node's data. So I don't want to get too bogged down on the mechanics of pushing and popping in a stack, because that's 222 stuff. I just want a class that we can play around with making generic. Node temp equals top of stack. Top of stack equals top of stack next. And then we'll return temp.data. All right, and we have garbage collectors, right? So I've got something pointing to the top of stack. I change top of stack here. I use temp data here, but once I exit from this method, temp was local to here. Temp is no longer a valid object, and that's the only thing that was pointing to that old TOS node. So that's going to get garbage collected. So just a thing in there. All right, so let's make our node class. So this is a string data in a node next. So that's a really easy class to define, right? And then let's go ahead and use this. So let's push some things onto our stack. And then we'll pop a few times and see what we popped off the stack. Don't forget to construct your objects before you use them. We're pushing this is a test, we pop off. A test is and this. Might not have been initialized. It's being polite, you know. You might want to check that. Alright, so there's our stack implementation for a stack of strings. Okay. Alright, so what do we do if we wanted a stack of integers, for example? So first of all, this has to change to integer. And then here, this string has got to change to an integer. This string has got to change to an integer. And that's it. Right? Those three changes from the word string to the word integer have now given me a stack of integers. And so if I push integer values, right, I've got my stack-like behavior working on integers. And if I wanted to make a stack of rectangles, I change this to rectangle, I change this to rectangle, and I change this to rectangle. So this is nicely set up for code reuse, right? And I could make, you know, string stack and integer stack and rectangle stack and have, you know, a whole directory of different versions of this, right? But a generic basically lets us use this one set of code, and the whole idea is when we construct our stack, we're going to do the following. We're going to say stack angle bracket, you know, some type like rectangle or string or whatever. And whatever type we put in here, rectangle, string, integer, that's what we want to put in right here, and right here, and right here. Alright, so how do we set this up? So making stack generic. In the declaration of the class, I'm going to put in a pair of angle brackets, and I can specify one or more parameters in here. Okay, and you usually see this done with like a T or an E or some single uppercase letter, but it's like a variable name. And the idea is when I construct my stack or I declare my stack, if I say stack angle bracket string, then in my code this uppercase T represents string. And if I say stack angle bracket rectangle, then this uppercase T represents rectangle. And so now I can come down to where I said integer. Instead of saying integer, I can say t. And instead of saying integer, I can say t. And you can almost think of it as like a pound define in C. It's not a preprocessor, but you can think of it that way, right? Whenever the JVM or the compiler looks at this and sees a T, it's going to use whatever was specified in angle brackets when I declared an object of type stack. So integer, string, rectangle, etc. All right, and there's logistics that there's things that need to happen here. So if I do this, I'm going to start getting a lot of errors, right? And that's because my node class is still returning an integer. So I need my node class to also be generic and say it's going to have a data field of type whatever t is, and then a next field of type node. And this takes a few tries sometimes to figure out the depth to which we're making this generic. So for example, when I declare a node, node is now generic. It needs to know what type of things are stored in the node. So this is a node angle bracket t. And this is a node angle bracket t. And this is a node angle bracket t. And now it compiles, but I'm getting a warning. All right. So when you get this message, it's saying that you're using something that you shouldn't be using. It could be deprecated, it could be something that's ill-advised, and so on. And it gives you a hint: recompile with -x_lint. So lint is a thing in C that you can use to basically analyze your C program and look for things that are kind of odd or quirky, things that might get you into trouble. And so delinting your code is getting rid of those little, fuzzy things that probably don't do any harm, but you really don't want in there anyway. So if I were to compile this with a -x_lint, I'll get some talk back. And it's basically saying, hey, I'm using a node in here and I didn't tell it what type of thing to construct with. Now, chances are if I go ahead and I run this, it's going to work fine, but get rid of these warnings, right? This is like Valgrind warnings, right? It's something that's not quite right. So in this case, right, when I declare an object of type node, I need to do that. I don't need to do that, but I need to do it when I construct. Alright, and I believe I'll still get warnings here. And the last warning is TOS equals TOS.next. TOS is a node of type T. Temp is a node of type T, which is TOS. Well, that's not where I was expecting an error to happen. T extends object declared in class stack. Alright, yeah, this is the tricky one. So in my node class, right, I have an object of type T, which is called data. I have a field called next, which refers to not just any old node, but a node of type T. I don't think it's a null issue in this case. I think it's just this. I said next was a node, but I didn't specify what type of thing. And again, when it runs, it will probably work, but specify it there. and then we'll get rid of our warnings. All right, so our main program needs to do the same thing. So when I declare a stack, I need to say stack integer equals new stack integer. And so now my stack class works fine. And now if I want a stack of strings, I just change my integer to string. And then I can push strings and I can pop strings. So that's how you can define generics yourself. And it's, you know, another form of code reuse, another mechanism that supports code reuse. Because A, you don't want to reinvent the wheel because it's more work. B, you don't want to have multiple versions of essentially the same thing, because now if you decide you need to make a change, you need to make a change to all of your similar implementations. And like this, if I decided I wanted to add something new to my stack, like an underflow prevention, I could change this one generic class, and then, you know, anything that's you know, using a stack, if somebody wants to use a stack of linked lists, they can do that. They still use the same code and so on and so forth. All right, so those are generics. Any questions about that? All right, we got about 5 minutes left, so let me just mention something here. So, you know, Java is open source. You can download the source code for Java, and you know, I pull this down as just a zip file. And it's you know, got 17,000 files in it. But this is you know, Java. This is all the stuff that we use. So there's the utilities. There was Java utility dot random and event listener, and there was a hash table, and all the stuff is there, right? I don't know how many lines of code, and I haven't unzipped it all, but 188 megabytes, and that's zipped. So maybe that's the unzipped size. So yeah, a few hundred megabytes of code. And I unzipped a little bit of this just to look at. So if we go like into the utility library, right, scanner.java. Well, here's the source code for Scanner. And, you know, copyright notice at the top, and so maybe it's not open source. Yeah, it's free software, GPL. And it imports other stuff, right? Because everything imports. I think this is just standard, not enterprise, if there's a difference. And, you know, it's all Java docked, so /**, this is the preamble, with, you know, markups inside. But this is, you know, the comment block at the beginning of the class file that describes, in your own words, what this class does. So a simple text scanner which can parse primitive types and strings using regular expressions. And it's a fairly detailed, they would probably get their 10 points of credit for this, comment block. And it's got a class that implements an interface, right, an iterator, and you know, it kind of goes on and on. So how big is this? This is 2,617 lines of code, and it's written in Java, right? Why not write something in Java if you've got it? And so, you know, if we had some question that we couldn't find an answer to about what something does, we could come down into the source code and look at it, right? So there's the preamble in front of each method, describing what it does, what the parameters are, what exceptions it can throw, things like that. And you know, that's the scanner class. Here's the linked list. So that's only 1,200 lines. And in the comments it tells us it's a doubly linked list. And it's abstract, right? So it's declared with this abstract type. And we can see where it's used. And it implements a generic list and a DQ and so on and so forth. So this is fun stuff to dig through, right? And you can see some of the stuff like we did when we wrote our own linked lists, right? Where we tinker around with previous and first and so on. It also keeps track of the size. So when you unlink the last node, it decrements the size and so on and so forth. It also keeps track of how many changes you've made. That's the modification count. And you can see all these details, right? Now, none of this is really relevant to us as users of a linked list, as long as we understand, you know, what the methods are, what the interface looks like. But this is the stuff behind the curtain, right? This is what's going on. And you'll see a lot of stuff, right? Here's a contains method, and it's one statement, right? It's less than half a line of code, but you know, it's got the whole comment block up here and all that kind of stuff. So it's cool stuff to look at sometimes. And this is size right 1, so that's a shift to the right by 1, which is a cheap way to divide something by 2. So most of this is Java. There are going to be a few things that that have to be done at a lower level. For example, when you create a socket, eventually that's something that can't be described in Java. It's something that's going to have to interface with, you know, an operating system level call. And so those can sometimes be done in a native language, possibly in C. But I don't know if those are contained in here or if they would be somewhere else. But anyway, if you're curious, pull down the source code and have a look at it. And it's kind of cool. All right, 5,000 lines for an integer. And an integer is, you know, a primitive type in C. In here, it's much more complex. And there's all kinds of things lurking in here, like these magic hexadecimal values, which are used for doing rapid conversions, and so on and so forth. All right, well, we're out of time. But anyway, so that's week 9. So Monday, we will do SLP presentations in class. So we'll take turns screen sharing, and you can do 5 to 10 minute pitch of your SLP. Make sure you turn in your final PDF report by 8 o'clock Monday morning. That's 70% of your grade, and then the presentation in class is 30%. And if you signed up to present in the morning instead, go ahead and show up for that, and then come to class, and you just kind of sit back and enjoy the other presentations. All right, have a great weekend. I will see you on Monday. Thank you.